speaking talks are 15 plus 3 minutes for discussions, followed by the last two talks that are 20 plus 5 minutes for discussion. And I want to welcome our first speaker, which is Chris Pollard, who's going to talk about measuring b-fragmentation in TT bar events with ATLAS. And Chris, why don't you take it away?
Okay, great. Let me. Yeah, Frank, if you just confirm you can see the slides again, I will get started.
I can see the slides.
Okay, cool. Thank you, everyone. I'm very happy to be presenting this because I was deeply involved in the analysis for the last couple of years, and it's really nice in ATLAS to get to present your own work sometime. So I hope you have some good questions at the end. So this is a measurement of b-fragmentation in TT bar events in ATLAS, as Frank just mentioned, and maybe some motivation before we get into the analysis itself. I don't think I have to convince people here, but B quarks fragmenting into hadrons is pretty interesting for a lot of reasons. Maybe first of all, pragmatically, b-hadrons leave a striking signature in the detector because they have a finite decay length, which we can resolve against the hard scatter vertex in LHC collisions. And what's more, there's a unique correspondence between the b-hadrons that we can detect in our detectors and the originating B quarks, which isn't, is true less and less as you get lighter and lighter quarks and hadrons. So you really can have a nice precision probe of QCD when you measure observables related to b-fragmentation. And then just some background, we currently tune our models in our Pollard shower generators and hadronization generators in E plus E minus theta generally from the Z peak from left and the slack linear collider. And then we basically extrapolate to the LHC environment when we want to look for Higgs to BB decays, top decays to B quarks, and so on and so forth. And one question the theory community has been asking for a long time is, to what degree is that correct? Are our models doing a reasonable job? And maybe kind of to muddy the waters a bit more, the plot on the right is showing a number of measurements and prediction coming from left and SLD, and also a couple of now somewhat outdated Pollard shower generators, but okay. The bottom line is there is some tension between the fragmentation measurements, the fragmentation measurements that took place as lepton colliders, and also the Pollard shower generators are not in great agreement in general, even in this day and age. So it's an interesting thing to kind of be probing and understanding to a better degree. I mean, there are a number of reasons why this is interesting. Higgs and top physics both depend on this quite critically. One really important analysis that we plan to undertake at the LHC for the next many years, probably, is measurement of the top quark pole mass. And ATLAS has shown, I think pretty convincingly, that one way to get it, to do direct measurements of the top quark mass is by using semi-leptonic or semi-muonic B decays in order to get a really clean final state that you can use to measure the top quark mass and not have to deal with the hadronic decay products of the B hadron and the surrounding hadronic activity. Of course, in order to do this, you really need to understand the B quark to B hadron momentum transfer very, very well. So this is one, I'll give you one example of an analysis where this is super important, but also more generally in Higgs and top analyses and in searches at the LHC, it's really critical that we understand b-fragmentation because this, our understanding of that kind of limits how well we can identify B-jets and reject charm and light jet backgrounds in our detectors. And what's shown on the right is a whole bunch of, these are B-tagging efficiency ratios. I don't want to go too much detail. The colored points are showing B-tagging efficiency predictions for a whole bunch of different Monte Carlo generator setups. And the black points are showing the measured efficiencies relative to the nominal generator. And what you can see is there's actually quite a large spread. And clearly the data are ruling out some of these models quite well. And so we wanted to turn this into a measurement so that we can start to get the feedback loop growing and improve the generator models for future analyses. So the strategy for this analysis, I think, is relatively straightforward, actually. We have a very large data set at the LHC with millions of TT bar pairs being produced and collected in ATLAS and CMS. In this analysis, we look for TT bar decaying to E mu BB final states because it's such a clean signature. Then we identify b-hadron candidates inside of our jets using the standard ATLAS secondary vertex finder. And then finally, we measure properties of the b-hadrons that we observe sensitive to the modeling of b-quark fragmentation, and we unfold these distributions back to the particle level for reinterpretation and for tuning. So maybe just very quickly, the fiducial definition we're using here is a little bit complex. So I just go through it quickly. We only treat B-jets coming from top decays in TT bar events as a signal here. Single top production also gives you a very similar signature, but for ease of interpretation, we've removed that because actually the theory community is still working out how best to give us a coherent prediction of TT bar and single top production. We ask for 1 muon and 1 electron in the detector. This reduces a whole bunch of electroweak backgrounds, which we don't need to deal with. And then we ask for exactly 2 B-jets that are in the fiducial region of the detector and at fairly high PT, so at least 30 GeV for the B-jets. And these jets that we're unfolding to are jets of stable particles, excluding neutrinos and prompt leptons. And inside of those jets, there needs to be exactly 1 electroweakly decaying b-hadron. And then we will measure properties of that b-hadron relative to the jet and the rest of the event. And you'll see throughout the talk, I'll use this observable named the charged momentum of the b-hadron, which is the first bullet point, and the charged momentum of the b-jet, which is that second bullet point. And these are built basically as the momentum sum over all of the charged particles with at least 500 MeV that either come from the b-hadron decay or are in the jet's catchment area. So given those 2 things, the momentum of the b-hadron and the momentum of the jet, or at least the charge components of their momenta, we measure a number of observables. 2 of them are shown on this slide. The first one is longitudinal Z, which is basically the momentum of the b-hadron relative to the momentum of the jet, but in the direction of the jet. And the second observable, this transverse Z, is simply the PT ratio of the b-hadron with respect to the b-jet. You can see a little cartoon of what I'm talking about for b-hadron and b-jet momenta on the left-hand side. But these are really sensitive to the momentum of the b-hadron relative to the local hadronic, the nearby hadronic activity. I mean, what we're really getting at is we're trying to effectively see what momentum fraction is the b-hadron carrying compared to the b-quark. Okay, and if you look in Pythia or Herwig or whatever, there will be model parameters that are used in fragmentation and hadronization models that are very closely related to these quantities. For instance, RB in the Lund-Ballard model, or the final state radiation, the alpha S that corresponds to final state radiation will change these observables quite dramatically. Another observable that we've unfolded here is a little bit more event-wide. We call it rho. It's shown in the top here. It's the transverse momentum of the b-hadron divided by the average momentum of the 2 leptons in the event. And the reason we do this is we don't have a really good control over the beam energy of the LHC. It's a hadron collider. So we can't exactly take the b-hadron energy and divide it by the beam energy and get a useful measurement. What we can do is kind of get a sense of how much momentum the b-hadron is carrying relative to the TT bar system. Or the energy scale of the TT bar system. And we use the 2 leptons, which we can measure very precisely, to kind of get that scale to which we normalize the b-hadron momentum. This is really sensitive to things like, again, alpha S in the final state, for final state radiation, but it's not at all sensitive to things that can affect the entire event, like ISR alpha S. Okay, but the point is, instead of just being a very local quantity like what was shown on the previous slides, we have these event-wide quantity that can start to probe also wide angle radiation that's taking place in the top quark decays instead of just local radiation, kind of in the fragmentation of the b-quark to the b-hadron. Finally, something that we kind of wanted to get a handle on more precisely at the LHC and in top decays is we're unfolding the number of charged stable b-hadron decay products, again with that 500 MeV cut. And the reason for that is we just want to make sure that our b-hadron production fractions, b-hadron species production fractions, are really compatible. Our predictions are compatible with what we see in the data, because that hasn't been measured previously. Okay, obviously the decay rates are very well known from other experiments, but the production fractions in top events, we don't know that well. Okay, so let's talk about systematic uncertainties before I get to the final results. Basically, the biggest uncertainties come from tracking efficiency and impact parameter resolutions in the inner tracker of ATLAS. We also have some rather large uncertainties coming from differences between different models of TT-bar production and decay at the LHC. So we take Pythia versus recent versions of Pythia and Herwig, and that ends up being, the difference between those two does tend to be quite large, actually. We vary alpha S in the parton shower. This has an impact on the measurements. B-hadron production fractions, the uncertainty on that does impact the unfolded measurement. And also we've seen for a long time at the LHC that the top PT and therefore the B-jet PT spectrum are not modeled very well by our predictions. So there's an additional uncertainty coming from the mismodeling of the B quark momentum. And then finally, for some of these observables, our inability to perfectly model pileups, so having many collisions in a single bunch crossing, we don't get that perfectly right. So uncertainties related to that can affect some of these observables. Okay, so finally the results that I want to highlight here. For this first observable, which is this Z longitudinal, which is shown on the left, this is the, again, the momentum of the b-hadron relative to the momentum of the jet. What you can see in the left-hand plot is we're getting something like 10% uncertainties on our unfolded data. Okay, and the very latest Monte Carlo generators are actually doing a pretty darn good job. These have been tuned to LEP and SL and SLAC on the Z-peak, and they're doing a reasonable job in an LHC environment. This is a little bit cheeky because we've taken tune parameters that we know are good, because we kind of, this was not done in blind by any stretch. So on the right, I've shown, for instance, some different curves of different versions of Sherpa and Herwig. What you can see is actually there are some rather large discrepancies over the last 2 years as these parton shower generators have evolved. Okay, so, okay, thank you. By no means have the generators been stable when it comes to B-fragmentation. We've kind of cherry-picked good ones on the left, but it's very nice to actually be able to conclusively say which versions of these generators and which settings are appropriate in an LHC environment. On the next slide, if we look at rho, which was more of this event-wide b-hadron momentum compared to the TT-bar energy scale or momentum scale in the event, we see something like 1 sigma tensions for the most recent generators, Pythia, Herwig, and Sherpa, shown on the left. They're not getting this quite right, so it needs further investigation. We don't want to make any strong claims about how poor this really is. But you can see if we, for instance, take our normal alpha S FSR variations, parton shower variations for alpha S, we do see rather large changes for this observable, so we can probably shrink these uncertainties a little bit for other analyses. And finally, this last observable, the number of charge decay products coming from the b-hadron is shown. Again, as expected, Pythia, Herwig, plus EVT-gen, and Sherpa are all doing a reasonably good job. Again, we've cherry-picked the left-hand plot a little bit. If you dig into the details, there were versions of Sherpa, for instance, which really were getting the baryon production fractions quite wrong. You can see the blue curve on the right-hand plot is really not doing a good job describing the data. So again, it's really nice we're able to constrain these fragmentation models quite well. On slide 13, like I said, now that we have observed data, we're able to pick out exactly the tune parameters that make the most sense. And this is really critical for these top mass measurements, which I said we want to get down to very precise levels of the HLHC, using, for instance, semi-muonic B decays on the left-hand plot and top to B to J psi decays on the right-hand plot for really lots and lots of data when we have very high luminosity. It's really important for us to understand the top quark to B quark to B-hadron momentum fraction transfers in order to get precise measurements of the top quark mass. Okay, so and I think we're going to have to continue to do more precise measurements of fragmentation in top decays in order to get the best top mass measurements from the LHC. And finally, on slide 14, recently Mitov and company showed, as far as I'm aware, the first quasi-analytic calculations of similar distributions, b-hadron production momenta compared to the surrounding v-jet activity in top decays. And this was shown in the autumn and top 2020. It's going to be really interesting to compare it to the unfolded data. There are some challenges that we need to take into account, which I've listed here. But I think you can see from the left-hand plot, the unfolded data, the uncertainties on the unfolded data are really quite small compared to the different orders of calculation that Mitov and company have been looking at, right? So I think we're going to be able to say something nice and have a nice comparison to their predictions. So just in summary, several different observable sensors of B-quark fragmentation have been measured for the first time in top decays with the ATLAS data. We made a bunch of comparisons to a lot of different MC generator predictions. We're going to provide a rivet routine and have data energies for the unfolded data so that people can use this to tune their own predictions. And I think this is going to be quite important as the LHC continues to collect interesting data. Thanks very much.
Thank you, Chris. We have a couple of minutes for questions. Like I said, please use the raise hand function or type your question in the chat box. Will.
Super, thank you. I apologize if this is a little bit of a tangential question coming from a heavy ion person, but I'm really interested in the possibility of people measuring tops in a heavy ion environment. So do you think this kind of measurement, there's a possibility for people to dig this out in, say, a lead-lead collision at ATLAS? Thank you.
Yeah, people are actively trying to do this. I think CMS have a rather convincing first, and someone connected might know better than me. I think CMS have a rather convincing first indication of top TT-bar pair production in lead-lead collisions. And yes, analyses like this are quite important if you want to be able to extrapolate back to the original B quark. You know, you measure, you find a secondary vertex, or you see a muon coming from a B quark produced in lead-lead collisions, and you want to know what the momentum of that B quark was based on the muon or whatever that you measure. Obviously, you need to understand B fragmentation very well, and that can be very interesting, obviously, if you want to see how much the B quark is interacting with the QGP. I haven't worked directly on this, but yes, people are trying to do these things and have been somewhat successful. But obviously, I'm not sure the fragmentation functions I'm measuring in this kind of analysis are really the biggest uncertainties for the QGP type studies, though. I think the underlying event in the lead-lead collisions is quite complicated and may lead to bigger uncertainties than the B fragmentation itself. But yeah, that's a long-winded answer. People are definitely trying to do this kind of thing in lead-lead.
Thank you, that was great.
Okay, I think we are running out of time. So let's thank Chris again for a very nice talk. And thank you. We will move over to the next speaker in this session, which is Keping Xie, who will talk about heavy flavor production at hadron colliders. Can you share your screen with us? Okay, I'll give you a heads up 3 minutes before the end of your talk. Go ahead, Keping.
Okay, thank you. Thanks for everybody to here to listen to my talk. This work is done with two collaborators. One is John Campbell in Fermilab, and one is my PhD advisor Pollard Study at SMU. The main result is done by 2 years ago, which included in my PhD thesis, but we are still working on improving the result and the write-up for the papers. So just a simple introduction, this work we will contribute to, this work will also contribute to the heavy flavor productions for this slow mass energy frontier 03 and 06. And we have a Help4G website to collect the results there. And shared our results, especially our grades. So that would be very useful for the future calculations or other process. So then we have come from the heavy flavored hadron colliders for the motivations. Currently, we have a lot of heavy flavor data accumulated in the old colliders or also in the new colliders, LHC especially. And from theoretical point of view, we have the heavy flavor production is a very good field for us to test the perturbative QCD and such as related to the factorization theorem or scale uncertainty about the calculation of fragmentation, etc. From the PDF point of view, the forward heavy flavor production at LHCb will probe the gloom PDF at very small x values, which is unprobed from other experiments, such as I just to show a very naive estimation about this B quark production at LHCb. And with this forward rapidity up to 2.5, we'll approach this 10 to -6 for moment fractions. That's very useful for us to constrain the heavy for the PDFs at small x. So from theoretical calculation for the heavy flavor productions, we have fixed flavor number scheme, which is very universal, allows everybody can do these calculations for 3 flavor for charm production and 4 flavor calculation for bottom productions. In fixed flavor number scheme, for consistency, we need to treat the alpha rounding and PDF consistently, such as for 4 flavor scheme for bottom quark productions, we need to assume the heavy flavors, heavy quark approximation, and this does not include this heavy quark in the rounding couplings, like this the virtual loop is mesons. And also because you have low heavy flavor PDF in the fixed flavor number scheme, so you have low flavor excitation contributions. But for public codes like MCFM or MetaGraph or PowerHack for the heavy flavor productions, really, we just use this PDF provided from LHCb PDF format, which is usually 5 flavors scheme in the alpha rounding, but low matrix element for this heavy flavors excitation term. Excitation because low heavy flavor PDF included in the matrix element. So there is inconsistency for the public code if we do this naively. So we need to deal with this probability that's coming from our scheme. It's called for heavy flavor production. It's called general mass scheme for variable flavor numbers scheme. So the scheme works in this way. When the energy scales, like your inverted mass of your heavy quark pair or your transfer or Earth momentum is low. When compared with your heavy quark mass, in these regions, mainly it's heavy flavor produced by flavor creation term. And in these regions, we expect that fixed flavor number scheme will work very well. But when your energy becomes much larger than your heavy quark mass, that's really happen at LHC. So the flavor excitation term will come in enters. And in this scenario, we will expect that the heavy quark mass can be ignored. So we will expect this will, in these regions, the zero mass scheme will be works very well because the heavy quark mass, heavy quark PDF, the large logarithms we summed into your heavy flavor PDFs. But transition from these two regions, we need to match from the low energy side to the high energy side. That's why we need this variable flavor number scheme. And in order to deal with the mass correctly, so we need to treat the mass correctly corresponding to general mass. So the basic idea for this general mass scheme, general mass variable flavor is it's sum over the flavor creation term in the fixed flavor number scheme and the flavor excitation term. There is overlap between these two contributions. So we need to subtract the double counted term, which called the subtraction term here. I call CB. You can see that I show some we presented diagrams here for the heavy quark production LHC. At the leading order of flavor, or the leading order of flavor creation term, you have quark pair productions. At the high energies, you have a flavor excitation directly coming from your heavy quark PDX. But at the next leading order of your flavor creation term, your heavy flavor PDF will be double counted in this flavor excitation and flavor creation term at the next leading orders. That's corresponding to the last diagram. So we need to subtract this over double counted term order by order. That's how this scheme works. So let's compare just to different variable flavor number schemes, several of them like this FONLL. Which is used in MMPDF, and there is also a code called GMVFNS. And very recently, it's just 2 years ago, similar, roughly the same time as what we have done. A new scheme called SR called MT scheme came out, similar to the simplified Eckhart scheme and Chi scheme. Chi scheme is the one. In this scheme, they choose the empty dependence of the low energy in kinematics in moment fraction for their flavor excitation and subtraction term. But in our scheme, we did do it very differently. Is that we choose this, we treated it for the massive phase space to deal with the flavor excitation and subtraction term. And in this approach, we will obtain a very good cancellation for this flavor excitation and subtraction at low energy. And the instability between these two terms will be tamed by the massive phase space. Here I show you what I have said here. So you can see I show this flavor creation term corresponding to fixed flavor number scheme. And for this flavor excitation and subtraction term, if we use this massless scheme, which is usually at high mass regions, it works. And in this one, and when you extend to this transverse mass of bottom quark to be 0 limits, you will see that the cross section is diverging. And in principle, this diverging in both pieces should be cancelled. But just because this divergence, the behavior makes this cancellation become very unstable. So you can see in this ratio plot. But with this massive phase space scheme, both of the flavor excitation and the subtraction will tamed, and then you will obtain the instability will be treated in this way, and the cancellations are great, and the cancellation you expect will works very well. Here we show that this you can see one thing is about this matching the massive subtraction term. In the low energy limits, you will see that the subtraction will cancel your flavor excitation term. At high energies, the subtraction you will expect it will approach to a flavor excitation term, and this magenta and this black curves coincide. And in this region, which is leave out for the green curve, which corresponding to the flavor excitation term. That's how this matching or asymptotic approach works. But in other way, in other scheme, like that FONL, they deal with this. They deal with matchings with the two and function with this the GM, and force your mass, force your cross section to be go to 0 doing these matching functions. For this code for GM VFNF code, they cannot deal with this property for PT go to 0 limits. So in this scheme, they just to treat as a hard card to require your transference mass to be larger, so roughly compared with your heavy flavor mass. So this is comparisons. So for this, our developer this scheme SR code MPS scheme compared with the existing data, like we have calculated this B quark production at LHCb. We compare with this the existing 7 TV and 13 TV data. Here we show this ratio plot. We normalize to this our theoretical prediction. We found that our theoretical predictions suffers large uncertainty, mostly from the scale uncertainty. Scale uncertainty, which shows as this the red curve, the red bands. And with this band, we can get a good agreement for the data, but this uncertainty should be treated in order to get better understanding about theoretical calculations. So, how do we deal with these uncertainties? One approach is that because the scale uncertainty is correlated, heavily correlated between different measurements. So one approach to treat this one is take the ratio observable. Like this, we can take the ratios between different energy, collider energies, and look at the ratio observable compared with our theoretical calculations. Here I show you one, the PT distribution ratios observable for 13 and 70 ways, and compare with the data and the theoretical prediction. With this ratio observable, you can say on the right hand side, I show this the different resources of these uncertainties. You can see previously the scale uncertainty dominate, but with this ratio observables, this the uncertainty cancel largely, and now after this, the biggest uncertainty remains coming from the PDF. That's the main idea, to invoke this observable to constrain the PDF uncertainty. So let's say what's the impact to this PDFs. So we just use this heavy B quark production from LHCb and use this ratio observable to say its impact to this CT14 PDF. We use the fast profiling and Hershey profiling technique with the AE pump. This allows us to see the impact when we add this data into the global phase and to see the uncertainty shrink or the central values, central phase. And on the left pole, so you can see that with adding this new data, so we see that the PDF gloom, PDF as low X will change just because of the impact of this data. And because the data is not so precise, and our CT1814 predictions give a good agreement describe the data, so we will not expect too big impact. And when we compare the uncertainty bands on this right plot, you can see the red curves compared with the blue bands is roughly almost the same way. Then that's because the experience uncertainty is still large. But if we can assume we have a bigger weight of this data, or we can have more precise data. Here we show that we increase the weight of this data to be weight like 10 times of 10 weights, and we can see that the uncertainty at the lowest value indeed shrinks. That give us the promises of this to constrain the gloom PDF, the low X value with this data. So let me summarize what we have here. So we developed this SR called MPS scheme for heavy flavor production and the hadron colliders. And we obtained good cancellations for both asymptotic limits. As I explained to you, the low energy limits, the subtraction term will cancel your flavor excitation term, and then the flavor creation term will remain, which corresponding to will return back to fixed flavor number scheme. The large energy, the subtraction will expect to cancel the flavor creation term, and this will go back to the zero mass scheme. Yeah, and our scheme will transition between these two schemes and smoothly. Our new calculation, is implemented in the MSFM, and then Monte Carlo generation is implemented in the 4 differential ways. Also, we have obtained the subtracted PDF and residual PDF, which can be easily calculated subtraction terms, and the difference between the flavor excitation and the subtraction term, which are available on half forges. So with this subtraction PDF and residual PDF, this can be easily applied to other heavy flavor processes, like the Higgs or Becker boson plus heavy flavor productions. Similarly, we can also extend our calculation up to NNLO, or when we have the appropriate matrix element, and also for the appropriate subtracted and heavy residual PDFs. Our calculation agree with this, the measurement of currently allows, and we in the future with this, the data accumulate and the systemic uncertainty reduce, we will expect this heavy flavor production and heavy hadron colliders, I have to say especially, will constrain the heavy flavor glue and heavy flavor PDF, especially at low small X regions. And also the last one, we have generate the fast computation grids that can be easily implemented in the global analysis. That's leave for the future studies. So that's all for my talk. Let me take questions here.
Thank you, Keping, for this very nice talk. Again, if people have questions, use the raise hand function in Zoom or write your question in the chat box. I see Hanu, you have a question. Please go ahead.
Yeah. So the data you have, the LHCb, that's for B mesons. But if I understand correctly, the calculation you do is for B quarks. So yes. How do you deal with the B quark to B meson fragmentation in your framework?
Yes, that's a very excellent question. In our framework, we just assume a simple branching fraction from the B quark fragment to the b-hadrons. And in this approach, so that's doesn't for the absolute cross section, the predictions we need to use that. And in the ratio observable, this branch fraction will cancel. So we just directly take the ratio. That's our main focus.
Okay.
Are there other questions? Will, you raise your hand. Go ahead.
Yeah, just very quickly. So whenever you, in your motivation, you said you can get down to potentially x of 10 to the minus 6. And whenever I see x is that low, I immediately think about saturation. So could you comment on whether you see any hints of saturation at this point, or whether there's you have some hope that you might see something in the future? Thank you.
Yes, that's out of our calculation, of course. So the saturation, we do expect that at the very low x values, we have some impact. And we in our CT18, not in this work, but in our CT18 framework, we have a separate set called CT18X. That's especially incorporated the saturation models. And we will need to combine this both. First one from this our calculation from the hadronic, from the hard part calculation, but the PDF part, the small x part, we need the correspondingly a special treatment. But that's not in this work.
Okay, I see there are other questions, but I have to unfortunately stop the discussion because we have only 3 minutes for it. So I propose by you that you make contact Keping offline and follow up on the question. Let's thank Keping for this very nice talk, and we will move on next to Zhiyu Xiang, who will talk on b-hadron and quarkonia studies at the LHCb.
Yes, shall I begin?
Yeah, please go ahead.
Okay, thank you. Okay, hello everyone. The topic of this talk is studies of b-hadrons and quarkonia at LHCb recently. Many b-hadrons and quarkonia results have been published since the last DIS meeting. The eta-C parameter hadron production first measured at 13 TeV. The result shows consistent with color singlet model prediction. And then we observed the X3842 by fitting D0, D0 bar and D plus, D minus spectrum simultaneously, which are compatible with precise 1D charmonium state with JPC is 3 minus minus. And then in Xi0 K minus spectrum, we see 4 narrow peak structure, similar with the previous discovery of 5 narrow excited omega C states. It's possible the nearly angular momentum over radio excited omega B states over more higher states with pi0 missing in decay. And also for the reconstruction of lambda b pi pi with lambda b to lambda c pi over JPSI PK, a new wide state seen below the higher mass range, consistent with a broad axes reported by CMS. By fitting both lambda b pi pi spectrum with two different lambda b decay, the mass central value is 72 and width is 72 MeV in agreement with lambda b2s. Today, we focus more on recent results, which are listed here. Most of them are first observation. Firstly, a new Xie B star zero baryon was discovered with Xie B minus pi plus reconstruction, where Xie B minus formed using Xie 0 pi over Xie 03 pi. A new Xie B star baryon observed with a statistical significance of 10 sigma. The simultaneous fit show its value, its mass value is 6227 and the width is 18 MeV, which are consistent with being also spin partner of Xie B 6227 minus. Take into account the ratio of fragmentation fractions of B2 Xie B star and Xie B minus. The branch ratio has been reported and it's also consistent with the isospin partner Xie B 6223 minus. Sorry, 27, yeah. Based on high purity B plus sample using B plus and prompt cation decay model, we see peak structure around 300 MeV above the BK threshold. We tried 1 peak and 2 peak fits in PT beams of the prompt cation. The significance of a 2 peak structure relative to a 1 peak hypothesis above 7 sigma. And we found the central mass values of these 2 peaks is 66T3 and 6114 MeV. Of course, the single resonance which can decay through both BK and B star K channel cannot be excluded. Then a new semi-leptonic decay model from B sub S discovered. Take the normalization channel B sub S to D sub S minus mu nu to reduce systematic. The corrected B sub S mass allows to discriminate between signal and background, where the transverse momentum is the momentum of K mu pair transverse to the B sub S flight direction. The fit template from simulation, we obtained about 6,000 signal in both low and higher Q square range. As an example, the high Q square range fit shown in left plot. The Q square range means B sub S to K momentum transformation. And in total, 200,000 normalization candidates are obtained as shown in right plot. The B sub S to K mu nu branch ratio relative to B sub S to D sub S mu nu reported in low and high Q square range, and also the whole range. This work also measured the CKM matrix elements ratio, VUB over VCB into Q square range. The last two uncertainties from the D sub S decay branch ratio and form factor calculation. The form factor choice also leads to different results in low and high Q square range. And the measured VUB-VCB ratio improves the average of the exclusive measurements. The result on high Q square range is more close to the VUB-VCB ratio from lambda b to p mu nu measurement. A new decay model of B0 decay to D0 bar Keping is also observed, as shown in a middle plot. The involved B2 CC bar S transition can be as an input to further spectroscopy study of CC bar over CS bar. Take B0 to D star minus D0 Keping as control channel to reduce the systematic. Its mass fit can be seen in right plot. The charmless background strongly suppressed by requires a flight distance significance to D0. A machine learning section further improve the signal purity, and D0 mass constrained to its known value to improve the resolution. Due to the same final states for signal and control mode, we applied the mass window on the intermediate D star minus to split control and signal modes. Here list the measured relative and absolute branching ratio. For lambda b decay, we see a hidden charm pentaquark in Xi or Xi lambda system. So what about Xi P model? So we search for the lambda b decays to Xi1 or Xi2 p pi model with the recent data sets. And finally, we found the Xi1 p pi model with a statistical significance of 11 sigma, as shown in left plot. The normalization channel lambda b to Xi p chi shown in right plot. Here, the Xi0 contribution is not expected sizable because it's suppressed with the QCD factorization approach and much smaller branch ratio to gamma Xi with respect to Xi1. We measured the ratio of branch fraction between Xi1 p chi and p pi, and also the ratio of lambda b decay to Xi2 and Xi1 for both p pi and p chi modes. Here so-called R2/1. It shows no suppression of Xi2 to Xi1, which challenges the factorization approach for lambda b decay. With limited statistics so far, no evidence for contributions from exotic states in Xi1p spectrum. We also interested in search for open charm pentaquark. The lambda b decays to lambda c kk pi is an ideal model. So we searched for it and also discovered this model. With the 3000 signal, we didn't see any evidence for exotic states. So just measured its branching ratio. Recently, LHCb performed the first search for W heavy baryon Xi BC0 while its decay to D0 point Keping. No significant signal is found, so set up limit on the production ratio relative to lambda b decay. Now a new search for Xi BC and first search for omega BC both decays to lambda c pi and Xi c pi present on archive. Also, no significant signal is found, so up limit set relative to lambda b over Xi b in same final states. In This fiduciary range, the pseudo rapidity from 0 to 4.5, and the PT from 2 to 25 GeV. The upper limit set according to the predictions of W heavy baryons. The mass from 6.7 to 7.3 GeV, and the lifetime from 0.2 to 0.4 picosecond. And the upper limit for Xie pi is from 0.5 times 10 to minus 4 to 2.4 times 10 to minus 4. And for the Xie pi model, the upper limit is from 1.4 times 10 to minus 3 to 6.9 times 10 to minus 3. So just a quick summary. LHCb has made great progress on studies of b-hadrons and quarkonia. The first eta-C production measurement at 13 T, we agree with the theory. And we first search for W heavy baryon and upper limit set. And also we first observed the X3842 excited omega b, lambda b, Kb and b subset states, and also new decay mode of B0 to D0, D0 bar K pi, b subset to K mu nu, lambda b to Kc1 p pi, and lambda c K pi. So I believe we can looking forward to more exciting news after LHCb upgrades. That's all. Thanks a lot.
Thank you very much, Zhiyu, for interesting talk and staying well within time. So we have time for questions. Again, use the raise hand or put your question in the chat box and I'll pick it up. Will, you raised your hand. Go ahead.
Yeah, super. Similar question to other speakers. So with these very interesting new heavy flavor hadrons, what are the prospects for being able to dig these out of, say, proton lead or moderate multiplicity lead-lead collisions with LHCb? Thank you.
Sorry, you mean which results?
So do you think it will be possible to measure any of these new interesting states in a higher multiplicity environment, say in a proton lead type collision or a moderate multiplicity lead-lead collision? Thank you.
Yeah, according to the recent measurement of the X3872, I think it's possible to do some kind of this study.
I think that would be very interesting. Thank you.
Any more questions? Okay. Not hearing any more. Let's thank Zhiyu again for a very nice talk, and
thank you.
We will move to our next speaker, who is Marat Siddikov. And Marat, can you share your screen with us?
Yes.
You have 20 minutes, and I'll give you a heads up 5 minutes before the end.
Okay.
Please go ahead.
Good afternoon, everybody. In my talk, I'm going to discuss production of heavy charm and bottom mesons and high multiplicity events. My talk is theoretical. Effectively, my talk summarizes results of several of our recent publications and archive reprints, and you may find technical details, which I'm going to omit obviously, in these papers and publications. I would like to start with a short introduction. According to modern conventional paradigm, we assume that production of mesons and hadronic states at high energies occurs via gluon-gluon or pomeron-pomeron fusions. We speak about pomeron just to reminds that high energies gluons vigorously meet other gluons and they hadronize, produce hadronic particles. Diagrams which include more than 2 pomerons or more than 2 gluons are usually disregarded because usually they believe that gluon densities are not so large. Besides, perturbative QCD, such diagrams are usually suppressed by LFS, and frequently we also have additional suppression by high twist. However, in the small X kinematics, the so-called BFK regime, we should be very careful because here gluon densities grow vigorously and potentially might compensate all suppression factors mentioned above. In case of inclusive production, we understand that both mechanisms potentially could contribute, and the situation is somewhat ambiguous. We cannot say reliably which of the contributions is more important. But we expect that in very small x, we come to what's called saturation regime. In this talk, I'm going to demonstrate that modern data on multiplicity dependence potentially could help us to clarify the situation and understand better the role of the 3 pomeron contributions. For the sake of definiteness, I will consider heavy quarks, and we know that for them, the hard scale is set by mass of the quark, which is a very large parameter. I will start discussion with GPSI production. Today, we know that production of GPSI from 2 pomeron fusion.
Marat, can I briefly interrupt you? Could you see maybe that you change the fit width that you have to fit height of the slides? And we are missing in your up. That would be very useful. Thank you very much.
Is it better now?
We can see the full slides now. Thank you.
Okay, thank you. Well, according to color singlet model, we expect that production of GPSI mesons from pomeron fusion should be accompanied by emission of soft gluons. And this picture was offered more than 40 years ago, and it can describe very well small PT and PT integrated observables. But it gives completely wrong behavior at very large PT. Today we know that we need to apply a non-relativistic QCD or NRQCD in order to introduce systematically non-perturbative long-distance matrix elements which describe the production of heavy quarkonia from 2 quarks. However, there are certain challenges, and we know them from the literature and could also hear during the talks of yesterday and today morning. One of the challenges is related to the fact that long-distance matrix elements, which are extracted from experiment, significantly depend on technical details of the feed, and the different groups got completely different values for this LD-miss. Besides, when we consider different quarkonia states, for example, psi2s, chi-c, and all B mesons, it was found that this LD-miss typically are much smaller than for GPSI. So the question arises, why GPSI is so different? Another challenge is related to the implementation of possible contributions of other production mechanisms, like, for example, co-production of charm, production by quark and gluon fragmentation, etc. To summarize, we believe now that understanding of GPSI so far is not complete. Now I'm going to discuss how the multi-pomeron contributions potentially could help us to understand what's going on with GPSI. Of course, when we consider just kinematical distribution of GPSI alone found in inclusive processes, we cannot clarify anything about 3 pomeron mechanisms, because we can always attribute possible discrepancy between data and theoretical expectations based on 2 pomeron picture to some new soft process where GPSI might have taken part. Fortunately, today we have also other possibilities to study GPSI production, and one of them is production of collective GPSI and other hadrons. This typically occurs when you consider inclusive production and start to analyze dependence of producer GPSI on multiplicity of co-produced hadrons. Actually, when we analyze experimental data, it's possible to analyze different setups when, for example, GPSI and hadrons are collected in different rapidity bins or in the same rapidity bins in order to understand the role of hadronization debris. Since we know from the theory the contribution of each individual pomeron to multiplicity distributions, experimental measurement of multiplicity dependence of the cross-section helps us to understand how many pomerons took part in formation of GPSI. Actually, these ideas are not quite new, and I think for the first time they appeared in papers of AGK, and since the time it was around but was not checked experimentally. We know that number of charged particles which appear in final states is proportional directly to the number of patterns which are processed from the gluon according to local pattern Harding duality. And we know also that probability of large multiplicity fluctuations is exponentially suppressive. Here we can see the typical expression given according to the so-called Kayano scaling. And we can see that it's exponential suppression, which is very strong at very large n. For this reason, in order to compare our different processes and understand what's going on at very large energies, it's quite common to consider instead the ratio of two different cross-sections at high multiplicities. Typically, this is done for the ratio of cross-section with production of meson to inclusive production of just n charged particles. If we interpret theoretically the cross-section as a probability to produce a given final state, then such self-normalized yields from a mathematical point of view can be seen as conditional probability to produce m in a given multiplicity class. Actually, such ratios have been studied in experiment, and it was found that in case of GPSI and d-meson production, they grow quite vigorously. If we had just conventional two Pomeron fusion picture, we could expect that dependence should be somewhat close to linear. And we can see that actually experimental data clearly indicates that this is not so. And potentially the signals that we could have contributions of multiple Pomeron mechanisms which are usually disregarded. Originally, this effect has been observed in AA collision, so it was touted as a QGP signal, but today it's reliably established that it also exists in PP, and so it's clearly not related to QGP. Now, before showing my final results, I would like to discuss briefly some technical details related to our evaluations. We considered the so-called CGC SAT or Count dipole framework. In the literature, it's frequently assumed that dipole cross-section, by definition, should be a universal object which takes into account all possible interactions with the target. And before we continue, I would like to revisit what exactly it includes and what it doesn't include. It should be included by hand. We understand that dipole amplitudes should satisfy a Balinsky-Korchakov equation, and for this reason, this effectively corresponds to resummation of fan-like topologies which are shown here. When we consider in evaluations some phenomenological parameterizations, like for example BCGC, we understand that they try to interpolate different asymptotic regimes of BK equation, and for this reason, they also approximately take into account such contributions. But they don't take into account in no way diagrams which include two or more attachments of Pomerons to quark-anti-quark lines. Extensions of this approach for the case of high multiplicity events has been discussed in the literature a while ago. And actually, it was found that the only thing which we need to take into account is that saturation scale in high multiplicity events will scale as shown here. Actually, Q squared grows linearly with n. But I would like to emphasize that this is for a single gluon shower. Now we are going to discuss multiplicity dependence of the whole process. We understand that there is a number of different possibilities to produce charged particles in final states, and we should consider them all. In addition to, for example, diagrams which I have shown here, when I consider wavy line as Pomerons, or cut Pomerons more exactly, we potentially could have diagrams which are shown here with additional blue lines, etc. But fortunately, it's possible to show that after resummation of all such diagrams, they will give some common factor P, which is the same for inclusive and GPSI production. For this reason, when we consider the self-normalized ratio, such common factor will cancel. And for this reason, when we analyze multiplicity dependence of this ratio, we should focus only on the cut Pomerons attached to heavy quarks. The results for multiplicity dependence actually depend on the way how we collect charged particles and GPSI hadrons. If we observe the situation in overlapping pins, then enhancement of multiplicity obviously should be attributed to all Pomerons which participate in the process. In contrast, when we consider beams very well separated by rapidity, then we can clearly see that only some of the Pomerons are responsible for enhancement of multiplicity. We know from theory that each Pomeron in high multiplicity events behaves approximately gives approximately factor n to gamma to the cross section. For this reason, clearly we expect different multiplicity dependence between what is shown in the left and right plots. Now, I'd like to mention another technical detail that when we evaluate the cross sections for three-polymer mechanisms, potentially there are a number of additional possibilities. That, for example, in addition to diagrams with this one, we should take into account also diagrams with additional production of gluon. And potentially such diagrams could interfere with leading order correction, as for example shown in this diagram. But fortunately, numerical evaluation demonstrates that for the case of non-polarized protons, these contributions vanish, and for this reason, we may disregard them. So effectively, the cross-section is the sum of these and these contributions. Numerically, we found that the three-polymer contributions are smaller than the two-polymer fusions as expected, and they give approximately 30 to 50% depending on kinematics. And here, for the sake of brevity and due to lack of time, I omit this detailed discussion. But what is important, they have faster dependence on multiplicity, and for this reason become very important at events with high multiplicity. In this plot, I would like to present our results for multiplicity dependence of GPSI. Here in the left column, we have data from LHC, and this is from PIC. We can see that data for LHC, these are for the forward production when GPSI is produced at forward rapidities and particles are collected at central rapidities. And here for the case when both particles and GPSI are produced at central rapidities. We can see that in the second case, dependence on multiplicity is much more pronounced than in the first case. We can see also that the two-polymer mechanism, which is marked here by 2 gluon and shown by dotted line, significantly underestimates the expected multiplicity dependence. In contrast, our theoretical approach based on inclusion of both 2 and 3 polymer production describes data reasonably well. We also check that for RIC, description is also quite reasonable, which implies that energy dependence is correct. So we can try to extend our approach for other quarkonia states, like for example psi2s, upsilon, and Xie A. So far there is no experimental data, but it's interesting just to have some predictions to check our theory. For S-wave quarkonia, such as for example upsilon and psi2s, we expect that dependence should be approximately the same as for GPSI. Though there are minor differences due to the fact that this numerical coefficient gamma effective has mild dependence on the site of quarkonium and the energy square root of S. But we expect that experimentals could be able to check this and see if it is so or not. In case of p-wave quarkonia, situation is slightly different. We understand that p-wave quarkonia has different quantum numbers, so production mechanism is also different. Precisely, we understand that we have dominant contribution from 2-polymer fusion, and diagrams with 3-polymer fusion are strongly suppressive. We actually checked that inclusion of only 2-polymer mechanism perfectly describes data both at small and large PT, and both at low energies at CDF and at high energies at LHC. As well, it can describe what is important, such observable ratio of Xie production different spin states. It's also it's very sensitive observable. Now I would like to present our predictions for the multiplicity. In this plot, I have shown multiplicity dependence of Xie mesons by colored line and by gray line prediction for GPSI, which we have seen in the previous slides. We can see that for Xie depends on multiplicity is much milder because we have just 2 polymers instead of 3. We also have shown here expectations for energy dependence and also have shown what dependence on mass. Effectively, this is for Kb. In all cases, we can see that our estimates based on simple N2 gamma give reasonable expectation, reasonable estimate for the cross-section. We expect that confirmation of this result would help to clarify the role of 3-polymer mechanisms in quarkonia production. Now, I'm going to discuss production of D and B mesons. Conventional in the literature is assumed that this process is dominated by scattering of gluon on polymeron or polymeron-polymeron fusion. The 3-polymeron contributions which we need to take into account when we try to estimate the role of such corrections are shown here by diagrams E and B, or clustered diagrams E and B. In case of E, we can see that actually we have 3 quark-polymerons, and effectively I can consider this as a cross-section of some genuine process. Here I can consider
5 more minutes, Marat. 5 more minutes.
Thanks. And in this process, I can see that only one of the polymerons is cut, and for this reason, it will have different multiplicity dependence. In this figure, I have shown the ratio of the 3 pomeron to 2 pomeron contributions, and dashed line corresponds to this one, and solid lines corresponds to the sum of this one. This one is negative and larger than this one. For this reason, this correction is negative. And we have found that for charm, the effect is pronounced, but decreases at PT. For B mesons, it's quite small. We found that inclusion of this term allows us to improve description of PT at description of PT depends on the kinematic small PT. So due to lack of time, I jumped directly to the discussion of multiplicity. We can see that actual description of multiplicity in this framework is quite decent when we take into account both 2 and 3 pomeron contributions. And we can see that experimental dependence clearly deviates from linear dependence, which is shown by dotted line. Finally, I'd like to discuss briefly single diffractive production. It's very interesting because potentially it allows us to understand better what happens with 3 pomeron fusion mechanism. Typically, a single diffractive production is characterized by rapidity gap between final recoil proton in the final state and produced hadronic states. And due to presence of rapidity gap, we expect that this diagram is the dominant contribution is given by this diagram. Actually, it's a 3 pomeron mechanism, although we can see that only one of the pomerons is cut. But when we take into account this cross-section, we should take into account that potentially there is a huge probability that after some secondary processes, the rapidity gap will be filled by products of secondary processes. So we should supplement this cross-section evaluation with additional gap survival probability factor. And this gap survival probability factor, the function input parameter B, is shown here. B is distance between 2 protons. And we can see that for typical B for the 1 Fermi, which most important, this gives suppression by up to an order of magnitude. At large B, as expected, the suppression is negligible. Here I show the ratio of single diffractive to inclusive cross-section, and we can see that the only data which are available from Tevatron, this RBB, are in reasonable agreement with our theoretical estimates. Of course, we understand that the cross-section will be suppressed at large PT because formula is a high twist effect. Now I'd like to present my last slide. It's single diffractive production as multiplicity depends for single diffractive production. This is for non-prone GPSI and this is for D mesons. Actually, dependence is the same, and we can see that it's much weaker than for the case of inclusive production, which is shown by green dots and green line. And we understand that this happens because we have just only one of the pomerons which is cut. Now I jump to my summary. We found that the 3 pomeron terms give sizable contribution in the LHC kinematics, especially for charm small PT. We found that inclusion of this data improves description of inclusive data and allows to explain multiplicity dependence in both ND and GPSI methods without any additional model assumptions for its description. Also, we made predictions and we hope that it will be possible to check them experimentally. First, we predict that S-wave quarkonia will have approximately the same dependence as GPSI and D methods. For P-wave quarkonia, we expect the dependence should be much weaker because only 2 pomerons participate in their production. And finally, the weakest dependence will be for single diffractive production, which is shown here. Thank you for your attention.
Thank you, Marat, for a very interesting talk. The table is open for discussions, questions. Again, use the raise your hand function or leave a message in the chat.
If no one had anything, I did just want to make a comment. Oh, no, please, somebody else go ahead.
I see Kazuhiro.
Thanks. So I have a quick question. So you showed the comparison between the PT spectrum Keping Xie and some data. So did you check? Did you compare your approach? Did you check whether your approach, 3 pomeron fusion approach reproduce the PT spectrum just side production cross-section in proton-proton collision, say at LHC at forward rapidity or central rapidity?
Understand. Thanks for the question. Indeed, I actually skipped this question. Skipped this discussion due to lack of time. We checked this multiplicity dependence, and we found that it gives a reasonable description. And for this reason, we believe that this description is correct. Actually, you might find posts with detailed comparison in this and this publications, the second and the third one.
Okay, okay, thanks.
Yeah, thank you for putting up that reminder about where we can find this materials, Marat. Thank you. Other questions? I thought, Will, you had a question?
I think I was just going to make a comment that I really enjoyed the talk, and I look forward to seeing data, I guess, from LHCb, which would investigate these higher p-state quarkonia production as a function of multiplicity. I think that'd be really interesting to see. Thank you.
Yes, indeed, it would be interesting if LHCb or some other collaboration will measure multiplicity depends, and just to see if these predictions are correct or not.
Okay. There's still some time if anybody has another question. I don't see any further questions. So let's thank Marat again for a very interesting talk. And I propose we actually carry on with the next talk. We're a couple of minutes ahead of schedule, but if that's okay with Ann-Kathrin, then we should just go ahead. Ann-Kathrin, can you share your screen?
Yes, you see my slides?
Absolutely, fantastic. Thank you. Go ahead.
All right, thanks.
Give
yes,
your heads up 5 minutes before the...
Perfect. Okay. It's my pleasure to present today ATLAS results with beauty mesons. A quick overview of the talk. I will give a very short introduction about the B-physics program in ATLAS. And then I will show 3 analyses that we've performed. One is on the relative B sub C over B production cross-section. There's a measurement of the rare decays B and B sub S to mu mu with ATLAS early run 2 data, but also in combination with results from CMS and LHCb, and the measurement of CP violation in B sub S to J psi phi decays. The B-physics program ATLAS is a general purpose detector. Nevertheless, of course, we produce a lot of B mesons. In run 2, 2015 to 2018, we have collected 139 inverse femtobarn of proton-proton collisions at a center of mass energy of 13 TeV. And with this high center of mass energy, we have also access to heavier B states, such as B sub S, B sub C. In principle, we are producing 2.5 million BB bar pairs per second, but well, most of them are very forward, and what we want to analyze, we actually need to trigger on, so our actual data set is smaller. A typical B-physics trigger is a low PT, very low mass dimuon trigger, and with these, we have recorded about 150 to 200 events with BB bar pairs per second. You see here a histogram of the trigger menu for B-physics and dimuon signatures from 2015, where we have dedicated triggers for J psi B and epsilon resonances. And yeah, all the analysis I will be showing are using these dimuon trigger signatures. And the first one is the relative B sub C over B production cross-section. That is an interesting measurement because B sub C is a double heavy meson, so it contains a sham and a bottom quark. And as studying the production gives us insight on heavy quark hadronization processes. Of course, it is very short-lived. In the analysis I'm showing now, we are identifying the B sub C via the weak decay into J psi pi, and J psi goes to dimuons. In ATLAS, we are also studying another decay channel, B sub C to J psi ds or ds star, which should come out also later this year. Yeah, the production cross-section is measured double differentially. Actually, we measure the product of the production cross-section times the branching fraction. We do this in two bins of the PT and the rapidity of the reconstructed Bs. And in both cases, we use a very similar decay mode, that is B sub C to J psi pi or B to J psi k. In essence, this measurement boils down by counting how many B or B sub C candidates we have reconstructed, and this gets then corrected for the acceptance and efficiencies for triggering reconstruction and selection. Our data set contains is a 20 inverse femtobarn data set collected at 8 TV. The B or B sub C candidates, the reconstruction starts from doing a vertex fit of the dimuon pair so that it is compatible with the J psi, and then we are adding another track. ATLAS has no PID for charged meson tracks, so we do a hypothesis of the mass of this track in the vertex fit that is being it a kaon or a pion. Background stems from partially reconstructed b-hadron decays as well as b to J psi pi for the B sample. And there is also combinatorial background from tracks and muons that come from different decays as well, we have a quite busy environment. The measurement is performed in the fiducial volume that is defined in PT and rapidity of the B candidates, PT larger than 13 GeV and the rapidity smaller than 2.3. We extract the number of reconstructed B and B sub C candidates in the fit to the mass, and that is also performed in these two bins of PT and the rapidity. You see the plot on the left-hand side is the reconstructed mass of B to J psi k candidates, and the plot next to it is B sub C to J psi pi. This is showing data from the complete data set, so the full fiducial volume. In total, we have there about 400K B candidates and about 800 B sub C candidates. And now I'm jumping to the results. I'm showing here the relative B sub C over B production cross-section times the branching fractions on the left-hand side in bins of PT of the reconstructed B and on the right-hand side in the rapidity. And the same is also given down in the table. The band that you see here, the black and red band, is the measurement in the full fiducial volume. What we see is that we cannot quite claim that we see a dependence in rapidity. Those two measurements are compatible within their errors, but it seems like we're seeing that the production cross-section of B sub C is actually decreasing faster with PT than the one of the B mesons itself. Overall, comparing to other experiments, we are complementary but also compatible with the results that CMS has published. We have a large overlap in the fiducial volume. They stop at a smaller rapidity. And LHCb has, of course, a very different, much more forward-going fiducial volume in their measurements. Moving on to the rare decays, B and B sub S decaying to muons. This is a flavor-changing neutral current process. In the standard model, it is mediated via loop and box diagrams. It is helicity and CKM suppressed, so it's really rare. B to mu mu occurs at branching fractions of 10 to the minus 10, B sub S to mu mu at 10 to the minus 9. That means with the very low standard model contribution, even small contributions from BSM physics might get easily visible, and so it's a really nice playground to search for this. So we are searching for deviations of the predicted branching fraction. The measurement is performed on 26 inverse femtobarn of PP collision data at 13 GeV. This is early run 2 data taken in 2015 and 2016. Again, this is triggered with a dimuon trigger. So you can see in the central plot, this is the dimuon invariant mass of B and B sub S to mu mu Monte Carlo. We are not really able, with our mass resolution, to disentangle the two. So we are performing a simultaneous fit of the two decay channels. The measurement is performed relative to a reference channel, that is B to J psi K, again J psi going to 2 muons. The invariant mass distribution of this is shown in the right-hand plot. It is a very abundant and very well measured and well understood channel. So it's very suited as a reference channel. A key ingredient to this analysis and to its position is the use of a boosted decision tree to separate the signal from the backgrounds. And so let's have a look at the background components that we're having. We have partially reconstructed b-hadron decays. Those come in mostly at lower dimuon mass. They are leaking into our signal region, as you can see in the left-hand plot. There's also peaking backgrounds that comes from B or B sub S decays to pions and kaons. And then the pi's or k's are misidentified as muons. And you can see in the central plot that these have actually a peak in the signal region that is shown with the dashed lines. Both these two background contributions are taken from simulation. For the combinatorial background, that is our dominating background in this analysis, we played a trick with the boosted decision tree. So combinatorial background is muons from different decays that just by accident look like our signal. For this, we have trained the boosted decision tree BDT. I'm showing here the output of this BDT. In green, you see a Monte Carlo prediction of the combinatorics, and that fits very well to what we expect in sideband data. That is the data that's shown. And in comparison, Monte Carlo for B sub S to mu mu signal is shown to emphasize that we have quite some discrimination power with this BDT. And the BDT output is then used to subdivide the signal region. We have defined 4 intervals in BDT. Each of these intervals has a constant signal efficiency, but of course, at lower BDT values, we have much more background than at higher BDT values. This you can also see in the plots of the dimuon invariant mass. They are ordered by increasing BDT intervals. And while in the first ones, it's basically only backgrounds, whereas in the higher BDT intervals, you can see that the background, the signal is nicely visible there. And the fit that is shown in these plots, we extract simultaneously the yields of B and B sub S to mu mu. And by that, we can then calculate the branching fractions. In the plot shown here, we have B to mu mu on the y-axis and B sub S to mu mu on the x-axis. B sub S to mu mu is the more abundant of the 2 rare decays. In the combination of run 2 and run 1, we have measured this with a significance of 4.6 sigma, with a branching fraction of 2.8 10 to the minus 9. For B to mu mu, we have actually a best fit value that is negative, so we were able only to set upper limits, 2.1 10 to the minus 10. If we now draw this in this 2D plane, The combined result is the black dot here. We see that we have quite a tension with the standard model. The deviation in this measurement is about 2.4 sigma. That makes it very interesting to gather more data. So ATLAS, CMS, and LHCb have performed the combination. This is not yet including the very latest results by LHCb. Would be interesting also to see this. In the combination, maybe just have a look at the right-hand plot. This is the combined result. Still quite a tension with the standard model remains. Here it is at 2.1 sigma. What will the future bring us here? In ATLAS, we have performed an extrapolation of run 1 results, so a little bit older than what I've shown in the previous slides, to the full run 2 and to the high-Lumi LHC expected data. So that means we have increased the luminosity, the center of mass energy, and adapted for detector performance and for triggering. For high-Lumi LHC, there is not yet the trigger menu out, so we have defined 3 possible dimuon trigger scenarios that give different yields. The plots I'm showing on the left-hand side, they are always centered around the standard model expectation value. The upper one compares the run 1 stats in blue to the run 2 statistics, where we would already achieve a very good measurement of B to mu decays. In the high-Lumi LHC prediction, we can further reduce the uncertainties by about a factor of nearly 2 and B sub S to mu mu and about 5 and B to mu mu. So stay tuned for this measurement. The next measurement I would like to show is CP violation in the decay B sub S to J psi phi. The CP violating phase that we're measuring here is well, the weak phase difference between the BS and BS bar mixing amplitude and the decay amplitude of B to CC bar S.
You have 5 minutes.
Yes, thank you. In ATLAS, we have measured this weak phase as well as the decay width and the decay width difference in the decay B sub S to J psi phi with a total of 80 inverse femtobarn. In addition, the other decay parameters were also measured of this decay, but I will stick here to phi S and delta gamma S. Again, this is triggered with the dimuon from the J psi to mu mu decay. The phi is identified by decay to kk. And what is important for CP analysis is to know in which state actually the BS candidate is produced. So was it a BS or BS bar that we do with opposite side flavor tagging? And then the extraction of all the decay parameters happens with a time-dependent angular analysis. So opposite side tagging, Bs are never produced on their own, always in the BB bar pairs. So to know the flavor of our B candidate at production, we can actually have a look at the opposite side b-hadron. This can be done by checking the charge of, for instance, leptons that come from a semi-leptonic B decay. But usually this has a bit of dilution from, for instance, U to B oscillations or B to C to lepton transitions. So we are actually more sensitive to this if we collect all the charges in a cone around our object of interest. This is called the tag charge. And this variable is then used to give probability how likely it was a B or B bar. We calibrate this with the self-tagging channel B plus minus to J psi K plus minus because the charge of the K-ion actually gives us directly the result if it was a B plus or a B minus. The calibration channel is shown in the upper plot. It is also very well understood and very abundant. In terms of tagging, maybe just have a look at the rightmost column. This is the tagging power. We have in the method where we use so-called tight muons, so muons that have a very high quality, they give us the best tagging power, but also contributions from low-petty muons as well as electrons and jets are non-negligible. And with this information, we can then perform the analysis. Well, B sub S is a pseudoscalar, decays into two vectors. So in the final state, we can have one CP odd or two different CP even states. And these can be distinguished with a time-dependent angular analysis. In addition, in the Sigma model, we also take into account interference from the decay from the non-resonant B sub S to J psi KK decay. And this is then fitted to the distributions of the B sub S mass, the proper decay time, and decay angles as shown here in the sketches. And these are the distributions that are actually fitted. On the top left, it is the reconstructed mass, next to it the proper decay time, and on the bottom, the angles. And this is the final results that we get. On the left-hand side, you see the comparison of the run 1 result in blue to the run 2 result in green and the combination in red in the plane of the CP violating phase phi s versus the decay width. And we see that from run 1, first of all, we have improved our precision quite a bit, but we have also moved a little bit away from the standard model prediction, that is the black rectangle here. This is actually apparently most obvious in the measurement of the decay width gamma s that turned out in run 1 to be deviating from standard model by about 3 sigma. Overall, though, we are consistent with standard model predictions, and we are also consistent with measurements by LHCb and CMS, as shown in the right-hand plot. And by that, I would like to conclude. I've given a short glimpse of the rich B physics program in ATLAS. There are much more measurements that are being performed. Also, some of them you can see in this conference. The results I've shown, they are all consistent with standard model predictions, although we see a bit of tension here and there. And yeah, the future will show, because the precision will improve with the full run 2 data set and with further data taking in run 3 and at the high Lumi LHC. Thank you.
Thank you very much for a very interesting talk. Are there questions? I see Daniel Greenwald, please go ahead. I think you can unmute yourself. Yeah.
Yes, nice talk, nice results. I'm just wondering on the B sub S to mu mu and B sub D to mu mu result that you showed, there's this negative correlation between the results, and then the final value for B sub S mu mu. Does this constrain B sub D to be positive, or does it not?
Say again.
The B sub S to mu mu result that's quoted, does it, this mean value plus or minus something, is this calculated constraining B sub D to be above 0, or is it taken in the full range shown in the plot?
I don't think so. We have a bit of correlation. No, there's no restriction. Otherwise, the best fit value would sit somewhere here, right? I mean, what we have, though, there is some correlation because of the mass resolution, and that's why you see like this this ellipsis being a bit tilted.
Because it seems there would be discrepancy to the standard model would be larger if B sub D was not allowed to be unphysical. Or is that the wrong interpretation?
I'm not sure, sorry.
Okay, thank you.
Are there other questions? we have a minute or so. But if I don't see any other questions, I would like to take the opportunity to actually thank not only Ann-Kathrin, but all the other speakers in this session for their very nice contributions. And unless I hear any comments from the organizers, I'll be wrapping up today's time slot in this session. And I'm sure I'll welcome you all back next, which is going to be tomorrow morning. Thanks, everybody. Bye-bye.
Sounds good.
Thanks so much,
Thanks
Frank.
for coming, everyone.
Bye.
Thanks. Bye.
Goodbye.